In this video, we're going to work some example problems on linear approximations and differentials. We talked about in the video where we go through this section of the textbook that this idea of linear approximations and differentials might seem pointless and kind of a waste of time, but remember, it has more applications in real life than you think. And some of the problems that we work in this video, like finding the square root of, like a number like 3.98 or something, in real life, you would never do that with a linear approximation. You would just use your calculator. But these problems are just designed to teach you the general idea, the general principles behind linear approximations. And then also outside of real life applications, you could be tested on this topic in your calculus class. So these problems will prepare you for the test. Okay, find the linearization Lx of the function at A. What does that mean, the linearization of a function? Well, you have a function and you effectively replace that function by the equation of the tangent line to the function at that point. And you say that that equation of the tangent line, you assume that that is the actual function in the region near that point. And that's a good estimate for the actual function. So all we're doing, Lx, is just the equation of the tangent line to this curve at this point. Well, we know how to find the equation of the tangent line. We find the slope of the tangent line at that point, which is just the derivative at that point. And then we have a point because we know the point. We have a point and a slope. So just make a line, make the equation for a line. So how do we find the derivative of sine of x at this point A? Well, that's easy. F prime of x is what? Cosine of x. So what is f prime of A? That's f prime of pi over 6. Okay, we're in radian mode. So, this is cosine pi over 6. .866. Okay, so this is our m, right? We need a point and a slope. What's the point? We have the slope, but what's the point? So what is f of A? That's sine of pi over 6. Okay, 0.5. And this is, as far as like the point slope form, this is y1. And what is x1? It's pi over 6. Right? That's the point slope form is y minus y1 is equal to m times x minus x1. Well, we have our point x1 and y1, and we have our m, 0.866. So y minus y1 is equal to m times x minus pi over 6. So y is equal to 0.866x minus 0.866 times pi over 6, 0.453 plus 0.5. So 0.453 plus 0.5, 0.047. So this is 0.047. So Lx is equal to 0.866x minus 0.047. Okay, that's Lx. again, what is this? This is just the equation of the tangent line. It's tangent to sine of x at this point. That's it. Okay, same problem, but now our f of x is 2 to the x power. What is f prime of x? d dx of 2 to the x. How do we take the derivative of an exponential? That's going to be natural log of 2 times 2 to the x. Okay, so what is f prime of 0? 2 to the 0 is 1, so natural log of 2. All right, what is f of 0? 2 to the 0 is 1. Okay, so we've got y minus, what is our y1? What is our y? That's f of 0 is equal to m natural log of 2 times x minus 0. Because the point is 0, 1. The slope is natural log of 2. So y is equal to natural log of 2x. Well, let's do this. Y is equal to x natural log of 2 plus 1. And so this is the equation for the tangent line to this curve at a is equal to 0. So just to do the official linearization, call that L of x. Okay, again, what is this saying? Remember what this is saying. This is more than just finding the equation of a tangent line to a point on a curve. That's the linearization of 2 to the x at a is equal to 0. You can use this function as an approximation for this function. Like we're saying that, what we're saying is that L of x here is approximately equal to f of x. At least in close to the point a is equal to 0. Right? This is a linearization at or around the point a is equal to 0. Well, this is a linearization at the point a is equal to 0, so we can approximate the function around a is equal to 0. Now, again, this might seem pointless and trivial. Just plug whatever we want into our calculator. Why are we doing this? 2 to the x power, just plug whatever plug 2 to the 0.1 into your calculator. This is good practice for linearizing something. This is more useful than you think in certain types of situations. Okay, verify the given linear approximation at a is equal to 0. Then determine the values of x for which the linear approximation is accurate to within 0.1. Okay, so they're saying that if you linearize this function at a is equal to 0, or like, okay, you linearize this function at 0. Find the equation of the tangent line to this function when the x is equal to 0, that's equal to x. So let's verify that. What they're saying is this is L of x and this is f of x. So what is f prime of x? That's 1 over 1 plus x. Okay, so what is f prime of 0? That's 1. Okay, what is f of 0? Natural log of 1, that's 0. So the point is 0, 0. The slope is 1. So y minus y1 is equal to m times x minus x1. Y is equal to x. Okay? Yeah. That's L of x. Okay, now determine the values of x for which the linear approximation is accurate to within 0.1. So how do we do this? Well, we need to solve this. So the idea is the absolute value of the function minus the linear approximation. When is this within 0.1? That's what we need. We need to. This is an absolute value inequality here that we need to solve. So if you remember from algebra, if we have an absolute value inequality, so the absolute value of some expression is less than a constant, then that's equivalent to this compound inequality. So that's equivalent to the natural log of, and then okay, so let's subtract this entire equation by the natural log of 1 plus x. So now let's multiply this entire inequality by -1. So we'll need to flip the inequality signs. So we'll bring this over to the first spot. We get so x is going to lie between, if you take the natural log of 1 plus x and shift it up by 0.1 and shift it down by 0.1, it's going to lie between those curves. Okay, now if we come to our calculator and we plot these functions, so natural log of 1 plus x minus 0.1, okay, okay. Now, if we zoom in, okay, so what is this point and what is this point? You know, you could try and solve x is equal to natural log of 1 plus x minus 0.1 and get this point, but we're doing this graphically. So, okay, we go analyze graph, intersection. There's the first graph, there's the second graph, and then the lower bound is here, upper bound is here. Negative 0.383, negative 0.383. So this is okay. Now we're going to do this again. .516. And there we go. So you could have used solve and then typed like x is equal to natural log 1 plus x minus 0.1, but then you would need to also specify like a lower bound and an upper bound. Compute delta y and dy for the given values of x, and dx is equal to delta x. Then sketch a diagram like figure 5 showing the line segments with lengths dx, dy, and delta y. So yeah, we're not going to sketch the diagram, but what they're doing here with this diagram, they just want to make sure you understand what exactly dy, dx, delta x, and delta y are. So these are the differentials. Dx and dy are the relative to the linearization. Delta x and delta y are relative to the actual function. And so since delta x is an independent variable, that's why dx is equal to delta x, because you're moving delta x or dx along your linearization or function curve. It's like that's based on the value that you specify. So like if you're trying to calculate the square root of 3.99, well, you're moving negative 0.01 along the x direction for the linearization or for the function. But the delta y is going to be the actual difference between the function value and the starting point. Dy is going to be the difference between the starting point and the linearization. So how do we compute dy, the differential dy? We we say dy dx is equal to what? Well, that's 2x minus 4. So what is dy? Just solve for dy. Now that's the function for dy. How do we actually calculate dy? Well, we plug in x is equal to 3, and this is dx, right? So you say 2 times 3 minus 4 times 0.5. So 6 minus 4 times 0.5. dy is equal to 2 times 0.5. dy is 1. What is delta y? Well, it's y evaluated at x plus dx minus y evaluated at x. So y evaluated at x plus dx is y at 3.5, and then y evaluated at x is y of 3. This is dy. So dy is equal to 3.5 squared minus 4 times 3.5 minus 3 squared minus 4 times 3. Well, actually, that's not right. So put a bracket around this. 3.5 squared minus 4 times 3.5, and then minus all of this. So minus 1.75 minus 9 minus 12. That's plus 3. So dy is equal to 1.25. Or no, I'm sorry. This is delta y, not dy. This is delta y. Okay, so there's dy, there's delta y, there's dx. Okay, and so what this means is that, just to kind of give an explanation of what they're asking here, if we graphed the curve y is equal to x squared minus 4x, and then kind of zoomed in around the point on this curve x is equal to 3, and then we also graphed the tangent line to this curve at x is equal to 3. Okay, then from 3 we went delta x, we went 0.5 from 3, so we went to x is equal to 3.5. So we're at 3.5. We're looking at the point x is equal to 3.5 for the function curve and for the linearization curve, the tangent line. We're going to see there's going to be a difference between a y difference between this function at x is equal to 3 and at x is equal to 3.5. That's what delta y is. There's also going to be a difference between the tangent line point at x is equal to 3, which is going to be the exact same because those both points are on this curve, and then the tangent line at x is equal to 3.5, and that y difference is dy. Okay, same problem. What is this? Is dx. What is the differential dy? Dy dx is right. So dy, the function, the formula for dy is Okay, now we need to solve for dy, so dy is equal to, we plug in x and dx. Three minus 2 is 1, so we get 2 over, and then 0.8 is 8 over 10, so this is so dy is 2/5. All right, now we just need delta y. So delta y is f of x plus delta x minus f of x. What is f of x plus delta x? That's going to be, so 3.8 minus 2, and then, okay, so 0.342. All right, that's delta y. Okay, use a linear approximation or differentials to estimate the given number. How do we do this? Well, our f of x, we're going to say is x to the 4th. That's our function. And we're going to find the linearization of this at x is equal to 2. Let's find L of x. So f prime of x is equal to 4x cubed. So f prime of 2 is equal to, 2 cubed is 8, 8 times 4 is 32. There's our slope. Our point is 2 comma 2 to the 4th, 16. So, okay, point slope. Y minus y1 is equal to m times x minus x1. Y minus 16 is equal to 32x minus 64. Y is equal to 32x minus 64 plus 16 is 64, 54, 48. That's L of x. That's the equation for the tangent line to the x to the 4th power at x is equal to 2. And remember what this means. This is we can just effectively replace this function by this. We're saying that L of x is approximately equal to f of x as long as we're near x is equal to 2. Well, we're close to x is equal to 2. So what is L of 1.999? 32 times 15.97. Okay, is that, how accurate is that? Let's 1 point. That's really good. At least accurate to 3 decimal places. Okay, same problem. We want to estimate e is equal to 0, e to the 0.1. So we're going our f of x is going to be e to the x. And we're going to do our at x is equal to 0 because 0.1 is right next to 0. So, okay, let's do the linearization. F prime of x is equal to e to the x. So f prime of 0 is equal to 1. Okay, that's m. So what is the point? 0, and then when x is equal to 0, f of x is equal to 1. So there's our point and slope. So we've got y minus y1 is equal to m times x minus x1. So y is equal to x plus 1. This is Lx. Okay, so remember, Lx we're saying is approximately the exact same thing as, well, it's approximately equal to f of x right around 0. So what is L of 0.1? 1.1. So we're saying that this is approximately equal to 1.1. Yeah, there we go. The edge of a cube was found to be 30 centimeters with a possible area measurement of 0.1 centimeters. Use differentials to estimate the maximum possible error, relative error, and percentage error in computing the volume of the cube and the surface area of the cube. Okay. So how do we do this? We're going to have a function for this cube, for the volume of this cube and the surface area. So if the side lengths are x, x, and x, what is the volume of this cube? It's x cubed. What is the surface area of this cube? Well, there's 6 sides, and each side has an area of x squared, so 6x squared. Okay, these are the formulas for the volume and the area, the surface area. What we want to do is we want to find the linearization. Like these are curves, right? We want to find the linearization of these at the nominal, like the nominal volume and the nominal surface area. So if we measured the edge of the cube to be exactly 30, you know, we get a volume at exactly 30. So we want to find the linearization of the volume function at x is equal to 30, and same with the area. So, well, actually, we're not going to find the linearization. We're going to do this in an easier way. All we need to do is to find the error. All we need to do is find the differential, dv. Right? If you think about the volume function, what is dv? That's the change in volume. That's not delta v. That's dv. Whenever the dx is 0.1, like that, you see, that's the error. If we deviate 0.1 from x is equal to 30, what's the dv going to be? Not delta v. We're trying to make this easy. What is the dv going to be? What is the dA going to be? Right? So dv is what? 3x squared dx. What is dA? That's 12x dx. Well, what is dx as far as differentials? 0.1. And now what is our x going to be? The nominal value is going to be x is equal to 30. So let's just solve for dv and dA. So dv is 3 times 30 squared times 0.1. So 3 times 30 squared times 0.1, 270. And that's going to be cubic centimeters. Okay. And then dA is 12 times 30 times 0.1. Okay, 36, that's square centimeters. And this is the maximum possible error. Right? We've deviated by 0.1 from 30. Now you could plug in minus 0.1, but in this situation it doesn't matter. It's plus or minus 270, plus or minus 36. But in another situation you might want to plug in. It might not be symmetrical, but it is symmetrical here. So That's the maximum possible error. Okay, now what is the relative error? What does that mean? Well, remember, you look at this 270. Wow, that's a huge error. But it's all about, it's relative to what is the volume, right? If the volume at x is equal to 30 is a million, well, then it's not that big of an error. So what you do is the relative error, you say dv divided by v. And we can do this in as far as a formula. Let's just plug this in here. So 3x squared dx over x cubed. And then so this gives us 3dx over x. So this is 3 times 0.1 over 30. And we've got 1/10 over 10. So 1 over 100. That's the relative error, but if you want to express that as a percent, that's 1%, right? This is 0.01, so that's 1%. So that's the percent error and the relative error. Now, if we do dA over A, we get, and then 6x squared. So 2dx over x. This is, so 2 times 1/10, that's 0.1 over 30. And so this is 1 over 150. That's the relative error, 1 over 150, and that's equal to 0.67%. So you see the relative errors are low. This might seem big, 270, but it's 1% relative error relative to the actual volume. One side of a right triangle is known to be 20 centimeters long, and the opposite angle is measured as 30 degrees, with a possible error of plus or minus 1 degree. Use differentials to estimate the error in computing the length of the hypotenuse. Okay. So we've got 30 degrees, 20 centimeters. This is 30 plus or minus 1 degree. So the hypotenuse is, we have sine of well, okay, no, we'll call this is theta. Okay, so sine of theta is equal to opposite over hypotenuse. Okay, so that means that the hypotenuse is equal to 20 over sine theta. But we know theta can vary by plus or minus 1 degree. So now, and nominally it's 30 degrees. So let's calculate. We're going to use differentials here. What is dH? Well, dH d theta is what? Well, what is the derivative of cosecant theta? Cosine theta over sine squared theta. So therefore, dH is equal to so we want to find dH, so we're going to make d theta 1 degree and also negative 1 degree and see what happens with theta equal to 30 degrees. Now we want to convert this to radians. So 30 times pi divided by 180 is pi over 6. And then d theta is plus or minus, so that's going to be pi over 180. So we can, okay, so that has a minus. So, okay, this is going to be minus. What we can do is make this a variable e, and now we want to evaluate e at x is equal to pi over 6 minus 2 root 3. Okay, now times, yeah, so that's, now if we, times pi over 180. Minus pi root 3 over 90. So minus 0.0605, or plus or minus 0.0605. That's centimeters. Wait, okay, no. So I need to add, if we look here, I need to multiply this times 20. I didn't put this 20 here. You see? So if we multiply this by 20, 1.21. Okay, so plus or minus 1.21 centimeters. That's the maximum error in the hypotenuse using the linear, using differentials. What is the percent error? Well, what is dh divided by h? We've got minus 20 cosine theta over sine squared theta d theta, and then 20 over sine theta. So we cross those out. So what we end up with is minus cosine theta d theta over sine theta. What is this? This is minus cotangent theta d theta. So minus cotangent pi over 6, and then times pi over 180. Oh no, this is cotangent. So cotangent pi over 6 times pi over 180. So 3%. Suppose that the only information we have about a function f is that f of 1 is equal to 5 and the graph of its derivative is as shown, the derivative. Okay? Use a linear approximation to estimate f of 0.9 and f of 1.1. So what they want us to do is, we have the derivative here, so we can get f prime of 1. What is f prime of 1. We're gonna do the linearization about x is equal to 1. F prime of 1 is 2. Okay, so we're going to do x is equal to 1. And we know that f of 1 is equal to 5. So we've got our slope and our point. So y minus y1 is equal to m times x minus x1. So y is equal to 2x plus 3. That's Lx. So, okay, so what do we do here? Part A, we just say what is L of 0.9? And what is L of 1.1? Okay, well, 2x plus 3, so 4.8. And then 5.2. That's the estimate of f of 0.9 and f of 1.1. Okay, are your estimates too large or too small? Explain. Well, I feel like we don't have enough information here because, okay, we know the derivative is positive. That's fine. So since it's positive, we know that the function f of x is increasing. But how can it be? It's going to be increasing in one of two ways. It's either going to be increasing like this, or increasing like this. So this is about the second derivative. The second derivative is going to be either negative or positive. This is the negative. This is the positive. If it's concave up, if it's positive, then the slope of the tangent line, the tangent line is going to underestimate. If it's negative, if the second derivative is negative, it's going to overestimate. So we don't have enough information. We need the second derivative to know that.